how does the way things are made affect how they sound? Please welcome Dr. Zoe Laughlin.
Okay, let's get that in place. Firstly, I'm so excited to hear Bob and the Iona's last presentation. I can't tell you, I'm like your dream member of the public. It was like, I loved that occasion, those 11 days, because I was like an outside broadcast geek, sending my mum pictures like, look at this, I put a camera here. All that, because I live near Lambeth Palace and I work at the Institute of Making, and that's up at Gareth Street. So my walk to work is always past Whitehall, and it was like daily interest. And one day I decided, well, I think I need to surreptitiously wear my BBC lanyard now so that I could keep walking up roads where I was not supposed to be and all this business. I had the time of my life and really enjoyed all of your hard work. So well done anyone and everyone involved in that. Anyway, that's not what I was going to be here to talk about. A bit of housekeeping first, which is there's a moment in my presentation today where I want you to eat some chocolate. But I first need to hand out this chocolate, okay? But I need to trust you not to eat it until I tell you, all right? So if you feel, I mean, the smell already is irresistible, but if you feel compelled, please don't, because you'll sort of miss out on the point of it later. But there's 3 groups. So this plate's kind of fatter. So we're going to get 1 plate going out in each section. Take a piece, and if you're happy to, pop it on your knee or on a bit of paper or something, and save it for the moment when you're told to have a piece of chocolate, okay? So that's the dark chocolate. Yeah, Dave, get that one going out that side. Thank you. Simon, you're on that one. So this isn't the presentation. This is just prep work. And then on this plate, there's milk chocolate. Please take 2 pieces of milk chocolate. That one's for your side. So 2 pieces of milk chocolate, 1 piece of dark chocolate. I think there'll be leftovers, but ideally we're after 2 pieces of milk, 1 piece of dark. And then tortuously sit there. It won't be too long till we eat it, but please don't eat it until instructed to do so. Okay. Oh, and my timer's ticking and I hadn't even properly started. All right. This is a presentation about materials and sound and some of the adventures I've had with materials, thinking constantly about what they sound like. But by background, I'm an artist. I went to art college, and then I did a PhD in material science and engineering in an engineering department. So I've sort of straddled these different worlds. And along with my friends and collaborators, Mark and Martin, we founded the Institute of Making in 2010 as a kind of expression of our interest in the made world. For us, making is the relationship between materials and processes, and what they get up to. So within the Institute of Making, we have lots of tools and equipment, and we also have our materials library. And the materials library is a collection of stuff that we've gathered over decades. You know, my baby teeth were kindly donated by the Tooth Fairy. They're in the collection. We've got things that were my grandfather's that were on, in his shed, things that were in Martin's studio, on Mark's desk. Like, it's a collection of very personal things, but it's there to tell stories about materials and processes. And one of the things that we're really interested in is that kind of sensory engagement with stuff, because it's a lot that can tell you about things through our sensory experiences of them. But to begin with, I just want to set the scene by thinking about the scale of space. So when we talk about materials, it's important to understand we have a human relationship to them, but actually there's big scales and small scales as well. There's things bigger than us that are important in the material world, but there's also things down inside the materials which are important. So this graphic essentially gives you a sense. There's no upper and lower limit to this, is important to note, but it gives you a sense of the scale of things. Like, culturally, we're sort of used to that idea that within biology there's things inside things, inside things, and that those structures give instructions. So, for example, in every cell of our body, you would find DNA, and that DNA would be instruction to say, oh yeah, when you grow hair, just grow kind of like curly, coarse, terrible hair. Like, that's information at one level that's affecting material at another level. But the same is true in the inanimate world. So the animate world has these scales that talk to each other, but the same is true of the inanimate world, the world of glass and metal and chocolate. Can I see you eating? And those scales affect what stuff's like, and they affect what it sounds like, it affects what it tastes like, it affects how bendy something might be. So for example, metals, okay, if you were to take a metal spoon and you zoom inside it, you actually, that one, you start to see metallic crystals. So all metals are made of crystals, and those crystals affect what it's like. And we'll come on to that in a minute. But also there's an important sense of that scale of space, zooming inness. There's also a scale of time, which is the duration at which you kind of investigate something. So here, for example, is time-lapse video of some silly putty that I've simply just put on a bench and filmed. But this is 5 hours condensed into 20 seconds. So you walk in and it's not moving, but if you speed up the footage, it's just like cake mix that we poured on the floor. So this is a viscous elastic liquid that flows incredibly slowly. So you'd speed it up and you'd perceive that liquidness. But when you look at it, it's just like a solid and you can knock it in, it's hard, you know. So you change the scale of time and you start to perceive the difference of materials. The same is true the other way. So I built an apparatus for breaking wine glasses with sound. And this is a kind of live performance at the Tate and also in the lab. So I looked at essentially different compositions of glass and how it breaks in different ways, because for me, damage is a huge revealer of materiality. How things break is a great way of working out what they're like. And one of the really great things about using the high-speed camera in this instance is that you'll see the top of this wine glass is moving in and out about a centimetre, perfectly comfortable. Like, glass is actually extremely elastic. It's also brittle, and it's easy to take it beyond its elastic limit, so we're used to it as something that smashes. But actually, there's quite a bit of bounce in the glass before the smash. So that changing of the perception of time, taking a fraction of a second and expanding it out, gives you that shift in the perception of time. But ultimately, in our world of humans, this is all about the stuff and things that we have around us and how materials affect them. So metals, just to give you a few examples and get a blowtorch out, because I did write the risk assessment, so I might as well. Is that on the side screens? Should be on the side screens. Yes. Let's get it in. Oh, hang on. No. Round. This way, that way. Yeah, that'll do. Okay. So we'll get back to metals. When metals go from liquid to solid, that's a process of crystallization. So a crystal nucleates, which essentially is born in the liquid metal, and an area starts to solidify. Another area starts to solidify. And that it builds up a crystal. And then other crystals are building up all at the same time, and then they start to mesh together and form this crystalline sort of structure. Think like ice crystals forming and snowflakes and things like that. It's that kind of crystal growth that forms. And the shape of those crystals, the orientation of those crystals matter for what something's like. So ductility, which we would call like bendiness, is all about crystals happily sliding over each other, right? When you want to make something strong and not bending, you need to change how the crystals are. So for example, in steel, you've got iron and the carbon atoms get inside the steel crystals and sort of just chub them out a bit, sort of swell them up, so that actually they don't slide over so easily anymore, so much so that you can now build a girder and make a skyscraper. But these crystals can do amazing things as well. So this is a metal that has programmable crystals. This means that the crystals can remember the orientation they were in when they were first born. When they first became a crystal, they kind of had neighbours they liked. I've bent it, it slid around. If I give it a bit more heat, they're going to go back to where they were when they were first born. So let's see if all that talk results in action. Ugh. Locked the blowtorch. His teeth wasn't in the risk assessment, but you know, okay. Let's see if I can get it to do it. Whoop. So yeah. So for those listening via radio, that is a piece of wire that was a random tangled shape. I've given it heat and it's turned into a paperclip shape. And suddenly it's recognizable as an object and a thing. And what I love about this is it speaks to the relationship between materials and objects every day. Like a paperclip, it's just like a little fart of a gesture of it's nothing, isn't it? It's just like, bleh. And most of the time it's only there to be unfurled and used to pick your fingernails or something. But it actually is a hugely perfect balance between material, form, and function. Like that little shape, just the right amount of tension in that shape. The steel's just the right stiffness and elasticity for you to open it up and put paper in for it not to flop apart. But anyway, what's happened there is I've made the paperclip out of a specific material called nitinol. So it's a nickel-titanium alloy. And the crystals have rearranged themselves. So that's metallic crystals. But then there's also objects like this that are a metallic crystal. So this is a single crystal jet turbine engine blade. So normally the crystals are teeny tiny, unimaginably small, okay? But in the case of this object, this whole part is one single metallic crystal, because this is made to be put into a jet engine, and in your jet engine you'd have rows and rows and rows of these blades all the way around, creating the kind of big fans that would be behind the really big fans at the front. So when you see the engine and you see those big fans, the ones at the front are there to suck in a lot of air and compress it down. Further back in the engine you have rows of these. You inject fuel, you ignite it, huge explosion, these wang around really fast, and off you go to New York or whatever. But the point is that's huge pressure, temperature, the centrifugal force alone, let alone the temperatures, would be an environment which any other metal that you care to name just couldn't exist in. It would just fall apart. So in order to, and that was because in those normal metals, like metals in general, you've got those crystals, and what you've got between the crystals is a grain boundary. That boundary is a potential crack. So in a high stress environment, that's a crack. So in the case of the engine, it all falls apart. So they had to make it as one single crystal. And they do that by essentially growing it in a really controlled way. They start down this end, solidifying it very, very slowly. The crystals start to grow. The crystals then, in an almost sperm and egg sort of race, set off up this helix. But because of the shape of the crystal arm and the shape of the void they're trying to move in, eventually only one crystal arm gets to the top of the helix, and then it solidifies this whole shape. So then they chop that off, and there's your metal object, but with no crystals inside. So you can get big metals, big crystals, small crystals. But I've got a picture on the screen of a, let's call it a tin can, right? But it's actually steel. But the reason that they use tin is that actually it's more inert, and a tin can that you might have soup in would actually have a thin layer of tin inside to protect the innards from the steel and the potential rusting that can occur. But tin does something amazing, which is the crystals of tin are a particular shape that when they slide over each other, they don't move easily. In fact, they catch on each other, so much so that they go... That was a really good impression. You wouldn't know, but it is. It's called the cry of tin, and it's essentially extraordinary because if you were bending it in your hand, it's kind of crispy and crackly, and it sounds like glass slash... I mean, it sounds crystalline. You can tell there's something inside it that's granular and that's cracking and crispy, yet it's just an ordinary bendy metal. But I'm using this as a segue into a project I did at the Tate that, it's too long to go into now, but one of the interventions I made was about sound, and we did an investigation into different works of art and the sounds of them and looking at the sound of art. But this was a work by an Italian artist called Manzoni, who back in the 60s did this famous work, Artist Shit, and it was like he made these, 10 cans of artist shit, and they were sold to galleries around the world. But he never said whether there really was poo in the can or not, but you had to take it as this sort of act, conceptually it was the idea of it as much as the reality, but maybe there is, maybe there isn't. That's all that kind of business. Anyway, so I thought, well, is there any way we could test? So we took a little UV light to it, looking for any biomatter, a little swab around the lid. But then little did the curators realise what they'd let themselves in for by giving me access. So what we did, holding a white glove, picked it up, gave it a little shake. And amazing. I was like, oh my God, it's granular. Because it like chick, 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 chick. Because in my head, I was thinking it was going to be like donk, donk, donk. Do you know what I mean? I was thinking turd, plog, blog, blog. Like I had this kind of vision of a pebbly-like thing in a can, and it would make that sound, but it didn't. It made this kind of granular shaky rice in a tin kind of sound. And so that was a big surprise. But then I thought, well, no, let's think about this. Because if you're going to put your poo in a can, what you don't want is for that shit to be wet, because the bacterial action is going to create gas, and you get anaerobic respiration in this sealed can, and give it a year and it's going to swell up and then it's going to explode. So if it is poo, it's definitely been dried out first. So there's tiny little turds on the wall in the Mediterranean sun. I can see this. I can see the drying out of the turds. You would put the turd in bone dry, but then it's very friable. So friable is that kind of crumbly. So yeah, maybe over like 50 years in a can, it might have just be dust. So maybe it is poo, because if you hadn't thought that through and you just put in a lumpy old bit of something thinking turd knot, it might have gone dong dong. Anyway, but sound is an amazing way of investigating and interrogating the world. And when you have material sensibilities, you're often thinking about the sounds things make. Like, we know how solid this might be. We know what this might be made of. You get a sense of the room you're in from the acoustics, I'm preaching to the converted. But there's a lot in which the investigation of sound and materials wasn't clear. So, for example, in science, they spend a lot of time denying the shape of things, and not denying like they don't exist type of conspiracy theory. What I mean is, like, if you're testing the strength of something, obviously you'll have this sample of a thing and you put it in your machine and it might bend it, blah, blah, blah. But you make this very abstract sample that fits in this machine, and also when you make an equation around strength, you kind of divide by area and length. Like, you want to take away the original shape. So it's not about how strong is that sample, but it's how strong is the whole idea of the material, right? But in not paying a close enough attention to the sample, you miss lots of attributes that actually come from shape. So I made some tuning forks of different materials as a way to really try to drill down into the effect of material on sound. So instead of having your tuning forks getting bigger and smaller if you want to change that pitch, I kept the shape identical and changed the material so that you can compare. Let's see if it does it. Here we go. Steel versus copper. So instantly less sustain. I'll just do a technique. Shit. Sorry. I've already said it once. Can you hear it? So copper, much less sustain, lower. And then you're thinking, well, they're the same size. They're just different materials. So that change in the sound is directly attributable to the copper. I'll play you brass. And this goes on and on. It has an amazing sustain. And you're like, well, yeah, I mean, entire sections of orchestras use this stuff, right? They know what they're doing. But actually, what's going on here is a relationship between elasticity and the density of the stuff. So it's like, how heavy is it? So how much energy does it need to get it moving? And then how wobbly is it of its own accord, I suppose, is how I'd put it in basic terms. So when you give it a thing and it give the thing equal amounts of energy by just whacking it on a table, the copper is much denser and less elastic. So not only does it take more energy to get it going, it just doesn't really, it sort of absorbs, it's softer, so it starts to absorb that energy and is just kind of like a lazy wobble. So that's a lower frequency. Whereas the brass is nice and stiff, and so it just goes on and on and on and produces a higher pitch. But it's that sustain is the really unusual thing, and that's to do with dislocations inside it, which is, again, back to the crystals. But the point I want to make is that the importance of shape in investigating some of these properties. Like, you might I made bells, tuning forks. I'm working on a cymbals project at the moment where the cymbal is designed to be both played and broken, so it's like a one-time only sound. But then this led on to, here's some of the bells, and then led on to spoons, like using other shapes to investigate other sensory properties. I'm looking at my time. Can I have an extra 3 minutes? Because I dilly-dallied at the start, and I haven't even got round to doing the chocolate bit. Yes is the answer, isn't it? Okay, so, because what things taste like is also designed, and it's designed for sound, and chocolate is designed for two big sounds. One is snap, right? But the other is, another bit, please, right? But this is because of its crystal structure. What I want you to do first and foremost is the milk chocolate. I want it on your tongue, no biting. Let it sit on the tongue, okay? On the tongue, close your mouth, warm it up. Let it kind of do its thing, okay? So you're not crunching. It's hard because you're like... But what first happens, if you close your mouth and you warm it up, chocolate is essentially... You've got cocoa butter, cocoa solids, and sugar crystals. And it's designed so that the crystals are of a certain size that they will melt really easily. The whole thing is designed to melt at body temperature. So already you've probably got a liquid forming on your tongue. And the saliva glands are going into overdrive. And you can go for it. You can just do what you want now. But the smell has been... The minute it starts to melt, the smell hits the back of your palate and is coming up into your nasal cavity, and you're getting a full kind of deliciousness experience, and it's absolutely designed to make you want another bit, right? So, but hold on, just hold back, all right? Because if you think about this, is a huge amount of engineering that goes into this stuff. Dairy milk in Australia genuinely isn't the same material as dairy milk in this country because it has to be designed to withstand different ambient temperatures. It's a different material. Now what I want you to do is try the dark chocolate, okay? Pop that on your tongue and do the same process. So instantly, I think you might find it's colder. It's sort of, you can tell it's harder, it's colder. You've got much less of the cocoa butter, okay? So it hasn't got that doesn't instantly collapse. It takes more heat to get this going, but bear with me because it's worth it. And you start to feel it melting. So in this case, the crystal structure is more stable, so it's less likely to melt in your hand and takes a bit more work to get going. But actually, it's more complex in the aroma compounds and things. So you're starting to begin to smell it. You can do a little bit of like rolling it around your tongue. Again, feeling that it's probably developing a liquid barrier around the edge. Now, I don't know if you're like me, just enjoy that while I tell you. When I was a kid, Easter was like the main chocolate harvesting period, wasn't it? That was when you got your main quota. And I remember my sister and I would have a sort of informal, unspoken, yet deadly serious competition as to who can keep the Easter egg going, you know, who can basically come out of July, I've still got Easter egg, you know. Like you'd have this kind of like unspoken competition of who can eke it out the longest. And I remember an Easter egg being produced in like August or something absolutely outrageous. Can we get the close-up camera on? And then my sister opened it up with glee, and then, aha, it's gone mouldy, like failed. She's failed. But it hadn't gone mouldy. What that chocolate had done is it had bloomed. So in its liquid phase, it had moved around, and the fats had clumped together, and the sugars had clumped together. And then it had re-solidified, because basically it got a little bit warm over the summer, and then it had set, I don't know, maybe she put it in the airing cupboard, who knows, but it had basically melted and re-solidified and reorganised itself into a different material. And you had the fats come to the top, the sugars separate, and it became different stuff. So this now can sit in my hand for days and it just won't melt because it's been reorganised so that the crystal structure doesn't collapse under the heat of my hand, unlike the stuff in your mouth. Right, now go to the milk chocolate, final piece, and just work out if it's as nice as it was the first time round. Potentially, this is now a bit sickly and a bit too sweet. And this is my campaign for essentially the Dark Chocolate Society, who don't sponsor me, but bloody well should, to say that actually it's a more sophisticated experience, and this is how you should eat chocolate. Chocolate shouldn't be kept in the fridge, unless you want that whole like chum, 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 chum mix, because when it mixes with your saliva, other things happen. But it is about a melting temperature and the aromas that release. But going to the other extreme of temperature, I did bring with me some liquid nitrogen because I was going to demonstrate the lead bell, and that when I freeze it, it actually can ring and make a sound. But I broke the container on my way here this morning that the lead bell can both be dipped into more safely. So instead I thought, well, let's make some ice cream, because I've gone to the trouble of getting the nitrogen, and this is also about crystals. So this will be the most delicious ice cream you've ever had in your life, but please eat it at your own risk, because although I have cleaned all this thing, you know, it's not a food kitchen, and these spoons are fresh out of packet, who knows what factory they were in, you know, the kind of thing. But if you would like to try this, you're very welcome. I'm going to make some liquid nitrogen ice cream. And what this is a game of is back to those crystals. This is a game of making unimaginably small crystals. So because this is minus 197 degrees Celsius, it will freeze the liquid at room temperature really quickly. Let's make raspberry flavour, why not? Mash that up. And the faster you can solidify something, so within the case of the metals, the same is true. If you take something from solid to liquid quickly, the crystals will be very small. So the opposite of the jet turbine blade, where those crystals were produced very slowly and it became really big. In this case, it's going to be really quick and they should be really small. I think we might want a little bit of honey, just, I want it to be nice. And it's not exactly raspberry season, is it? Oh no, hang on. No nails. Here we go. Oh, that's a bit much, never mind. You're only having a little bit. Mix that up nicely. Okay. Crap. I don't think that's going to do it. Okay. Right, so I better put on some safety specs because I did write that in the risk assessment. And the gloves. But what we're looking at here is the change of sound, okay? So listening, you'll hear the crystals forming and then cracking and separating from each other. You'll hear, well, let's just do some. So this is onto the ground. So you hear that, right? So the first thing there, you've got expansion of the gas hitting what essentially is a baking hot surface in comparison with the ground. So this is like pouring tap water onto a boiling hot plate. You can hear the bubbling. Hang on. But can you hear the tiny crystals forming, that crack? It's really important. I should have been stirring it, but I was too excited to show you that. See, if it was with chefs, I've had to have paid a different amount of attention to my technique, but I've just gone rogue here. And we're going larger planes of ice cream. But now, you can hear a granularity, again, which is the crystals. And there should be a sort of squeak from the metal bowl, but I'm not sure. Not quite getting that. Oh, there was a little bit there. Anyway, I've massively run over time, but I've given you chocolate, and now you can have ice cream for the quiz. So, how do we pass it round? I don't know. I'll just try a bit. Right, it's good. Right, it's really good. Thank you.
Dr. Zoe Laughlin, thank you very much indeed.